Welcome back to the deep dive. Tonight we're going into something that feels like, well, a bit of a ghost story for computer science.
Yeah, ghost story is a pretty good way to put it, actually.
Right. We're pulling back the curtain on the technology that's effectively eaten the software world over the last decade. We're talking about the engine behind ChatGPT, behind self-driving cars, behind the facial recognition that unlocks your phone in the dark.
And it's the technology that, everyone is using, but surprisingly few people know the actual history of.
Mm.
Because if you look at the timeline of innovation, it really shouldn't have happened.
That is exactly the mystery we are unpacking for you today. What if I told you that the most important idea in modern computer science, the one currently reshaping the global economy, was actually abandoned?
Yeah.
And not just once, but twice.
It really is a zombie story. We're talking about a technology that was literally left for dead, buried by the academic community. Funding was completely cut off, and then it somehow clawed its way back out of the grave to just conquer everything.
We are talking, of course, about deep learning. And our mission today is to figure out how that resurrection actually happened. We've got a stack of sources here covering everything from the AI winters to the specific technical breakthroughs in hardware and algorithms that made it all work.
And we're going to get into the weeds today, too. We aren't just doing the high-level fluff. We need to talk about the math, the specific hardware architecture, and the data. But we're also going to land on a really fascinating philosophical question later on called the hardware lottery.
I really love that concept. It makes you question if we're actually smart or just, incredibly lucky. But let's start at the beginning, or I guess the first beginning, because neural networks aren't actually new, right?
No, not at all. If you think this started with Google or OpenAI, you're off by about half a century. The first real wave of excitement was way back in the late 1950s.
Wow.
Yeah. There's a psychologist named Frank Rosenblatt who invented something called the perceptron in 1958.
The perceptron, it sounds like a comic book villain.
It does. It was a machine, though, a physical tangle of wires and potentiometers. It was effectively a very basic single-layer neural network. But the hype was off the charts. The New York Times actually ran a story claiming this machine would eventually be able to walk, talk, see, write, and even reproduce itself.
So the media overhyping AI is not exactly a new phenomenon. We've been doing this for 70 years.
The more things change, right? But here's the problem. The perceptron was really limited. And in 1969, the hammer came down. Two absolute giants of the field, Marvin Minsky and Seymour Papert at MIT, published a book called Perceptrons.
Right.
And it was devastating. It was basically a mathematical hit job.
What did they find? I mean, why did a single book kill an entire field of science?
They proved mathematically that a single-layer perceptron couldn't solve the XOR function.
Okay, let's unpack that for the software engineers listening. XOR is exclusive OR.
Right. It's a basic logic gate. Think of two switches. If switch A is on, the result is true. If switch B is on, the result is true. But if both are on,
the result is false because it's exclusive.
Exactly. And the problem is you can't draw a straight line to separate those answers.
Right. If you plot the inputs on a graph, so 0, 0, 0, 1, 1, 0, 1, 1.
Yeah, you cannot draw a single straight line that separates the true results from the false results. It is what we call non-linearly separable. Minsky and Papert showed that a single-layer network is a linear classifier. It can only draw straight lines. So it literally cannot solve XOR.
That seems, I don't know, that seems pretty fixable.
It is. You just add more layers. But the tragedy is that while Minsky and Papert were technically right about single-layer networks, the academic community read the book and basically heard neural networks are a dead end.
So they just threw the baby out with the bathwater.
Completely. Funding evaporated overnight. Researchers left the field to work on symbolic AI expert systems. This was the first AI winter.
But obviously they came back. We aren't using symbolic AI to drive cars today.
They did. In the 80s, we got the second wave. This is when backpropagation became popularized. We've discussed this in previous deep dives, but essentially it's the algorithm that allows the network to learn from its mistakes by sending the error signal backward through the layers.
Right.
It allowed us to actually train multi-layer networks.
Yeah.
And guess what? Multi-layer networks can solve the XOR problem.
So problem solved. The math works. AI takes over the world in 1986.
You would think so.
Yeah.
But then we hit the second AI winter.
Why? If the math worked, what was the actual problem?
The reality of the engineering didn't match the theory. These networks were incredibly slow to train. They were super finicky. And frankly, they just didn't work as well as other methods at the time.
Yeah.
If you were a working engineer in the 90s or early 2000s, you weren't touching neural nets.
Yeah.
You were using support vector machines, XVMs, or random forests.
Oh, man, I remember SVMs. They were the gold standard for a really long time.
They were elegant. They had beautiful math behind them. Convex optimization. That meant if you trained in SVM, you were guaranteed to find the global minimum, the absolute best solution.
Right, whereas with neural nets.
With neural nets, you might get stuck in a local minimum.
Yeah.
They were seen as this messy black box alchemy.
So if you walked into a tech conference in, say, 2005 and said, I'm working on neural networks, you were the weirdo.
You were the guy people actively avoided at the buffet. If you proposed a neural net paper at a top conference, people would politely smile and direct you to the poster session in the hallway near the bathrooms. It was career suicide.
That is absolutely brutal, but there were a few people who didn't give up,
A
right?
handful of very stubborn researchers, the godfathers as they're called now, Geoffrey Hinton, Jan LeCun, Yoshua Bengio, they kept the flame alive when it was deeply, deeply unfashionable, and history vindicated them spectacularly.
So what changed? We had 2 winters, decades of failure, and the smartest people in the room saying, don't even bother. What was the spark that turned this zombie into a superhero?
It wasn't one spark. That's the biggest misconception. It was a convergence, a perfect storm of 3 specific ingredients coming together at exactly the right time.
Okay, lay them on me. Ingredient number 1.
Ingredient 1 is my favorite irony in tech history. It's the hardware. But it wasn't hardware built for science. It was hardware built for teenagers.
You're talking about GPUs.
Exactly. Graphics processing units. In the 90s and 2000s, companies like NVIDIA were obsessed with one thing, making video games like Quake, Half-Life, and Call of Duty look better.
I definitely contributed to that R&D budget back in the day.
Huh. Well, you were inadvertently funding the AI revolution. You see, to render a 3D video game, you have to calculate lighting, shadows, textures, basically millions of pixels changing simultaneously.
Right.
To do that, GPUs were designed with thousands of very simple cores that run in parallel.
Versus a CPU, which has just a few really powerful cores.
Right. A CPU is like a team of 8 Nobel Prize-winning mathematicians. They can solve incredibly complex differential equations very fast, one by one. A GPU is like an army of 10,000 elementary school students. Individually, they aren't that smart.
But if you need to do 10,000 simple addition problems at the exact same time...
The elementary school students win easily. And here's the connection. Training a neural network is basically just multiplying huge matrices of numbers.
Right. It's all matrix multiplication, dot products.
Exactly. It turns out rendering pixels and training neural nets are mathematically almost identical. Around 2007 to 2009, researchers realized they could repurpose these gaming cards. They wrote code, specifically CUDA, to run their math on the graphics card. Suddenly, training that used to take months could be done in days. We're talking 10x to 100x speedups.
That is just wild. ChatGPT exists partly because kids wanted better frame rates.
It's a straight line from entertainment to civilization-altering tech. So that's ingredient 1. Compute. Ingredient 2 was fuel, massive amounts of data. In the 90s, datasets were tiny, maybe a few hundred handwriting samples. But then the internet happened. Suddenly we had Flickr, YouTube, Wikipedia. We had billions of images and documents.
And neural networks are hungry, right? They really need that scale.
They are data-starved beasts. If you don't feed them enough, they overfit. They just memorize the specific examples you show them and then completely fail on anything new. With the internet, we finally had enough food. And specifically, we have to mention ImageNet.
This was Fei Lai's project, right?
Yes. She and her team realized that algorithms weren't the only bottleneck, the benchmarks were. So they used Amazon Mechanical Turk to label 14 million images. It became the Olympics of computer vision. Having that benchmark was crucial because it gave researchers a common goal to chase.
Okay, so we have the engine, the GPUs, we have the fuel, the data, but the engine was still kind of broken, right? You mentioned earlier that the algorithms were finicky. What was the third ingredient?
The spark plugs, the algorithmic breakthroughs. These were technical tweaks that made deep networks actually trainable. Because before this, if you made a network too deep, if you add too many layers, it just stopped learning.
Let's get technical for a second here. Why did it stop learning?
It's called the vanishing gradient problem. When you train a network, you compare the output to the right answer, calculate the error, and send that error backward to update the weights. But for a long time, we used activation functions like sigmoid or ton, which squash numbers into a very small range, like between 0 and 1, or -1 and 1.
So as you multiply these small numbers together going backward through the layers,
They get smaller and smaller. It's like the game of telephone. By the time the error signal gets to the first layers of the network, the signal is basically 0.
wow.
Yeah, the network doesn't know how to change. It effectively dies.
And the fix for this was something called ReLU.
Rectified linear unit.
Yeah.
And it is laughably simple. The formula is literally just f of x equals max of 0 and x.
Wait, that's it. If it's negative, make it 0. If it's positive, just keep it the same.
That is it. But that simplicity meant the gradient didn't vanish. If the input is positive, the gradient is just 1. It stays strong all the way back. It made training deep networks computationally efficient and mathematically stable.
It's amazing that something so simple solved a problem that stalled the entire field for years.
Another big one was dropout.
Which sounds like what I almost did in college.
Huh. Well, in this context, it's a regularization technique. It stops the network from memorizing the data. During training, you randomly turn off or bench half the neurons in a layer for each pass.
Benching players.
Exactly. It forces the network to not rely on any single star player. It forces every neuron to learn something useful because its neighbor might not be there the next time. It makes the whole system robust. So you combine ReLU, dropout, massive data, and gaming GPUs, and suddenly the zombie is fully alive.
But there's a question here that I think a lot of people overlook. We call it deep learning. Why does the deep part matter? Why can't we just have one giant wide layer with a billion neurons? You said earlier that Minsky proved a single layer couldn't do XOR, but that was a small single layer. What about a massive one?
That is the million-dollar question.
Yeah.
And there is actually a theorem called the universal approximation theorem that says a single layer can theoretically learn any function, provided it is wide enough.
So why don't we just do that? Why deal with all these layers and vanishing gradients at all?
Efficiency. To represent complex real-world data in one layer, the number of neurons you'd need would be astronomical. It would be exponentially inefficient. Depth works because the world itself is hierarchical.
Unpack that. What do you mean by hierarchical?
Think of it like an assembly line. This is what we call representation learning. Let's say you're looking at a picture of a car. Layer 1 of the network doesn't see a car. It just detects edges. Horizontal lines, vertical lines. Layer 2 combines those edges to find curves, corners, textures. Layer 3 puts those together to find parts, like a wheel, a headlight, a window.
And layer 4 combines the parts to find the actual object, the car.
Exactly. And maybe layer 5 sees the whole scene, a car on a road.
So each layer is building a more abstract representation of the data.
Precisely. It's a hierarchy of abstraction. A deep network doesn't just classify. It builds an understanding of the world from the ground up. Doing that in one layer is like trying to turn raw iron ore into a Ferrari in a single step.
Right.
It's much, much better to have an assembly line where each station does one specific job.
That makes total sense. So we have the theory, the hardware, the data. When did the world finally wake up and realize, oh, wow, this is it?
There's a very specific date, the 2012 ImageNet competition.
This is the AlexNet moment.
The AlexNet moment. So for years, the error rate in this competition was stuck around 26%. People were using those support vector machines we talked about. Progress was tiny. We're talking 0.5%, improvements here and there. Researchers were fighting for inches.
Yeah.
Then Alex Krizhevsky, Ilya Sutskever, and Jeffrey Hinton showed up with a deep convolutional neural network.
What were the specs on that?
It had 8 layers, 60 million parameters, and they trained it on 2 NVIDIA GTX 580 GPUs for a week.
And what did they score?
15.3%.
From 26% to 15.3% in one single year.
It was an absolute annihilation. The gap between them and the runner-up was bigger than all the progress of the previous years combined.
It's like showing up to a bicycle race on a motorcycle.
It completely broke the competition. It was undeniable. Within 2 years, nobody was using anything else. Computer vision pivoted overnight. If you weren't using deep learning, you were competing.
And it didn't stop at vision, right?
No, it was a domino effect. First vision from 2012 to 2015. Then speech recognition fell. Do you remember how bad Siri used to be?
Oh, painfully bad. You'd ask for the weather and it would call your mom.
Exactly. Around 2015 to 2016, deep learning took over speech, and suddenly it just worked. Then came natural language processing, or NLP, with the transformer architecture in 2017, which led us directly to the large language models we have today. It was a conquest, plain and simple.
And now we are fully in the era of scaling.
The scaling hypothesis. This is the observation, championed by OpenAI and others, that performance follows a power law. If you double your compute and data, you get a predictable improvement in performance.
It's almost like physics.
It really is. It turned AI research from a search for a magic algorithm into an engineering and capital challenge. Just add more GPUs.
And here is where I want to get to that philosophical point you mentioned earlier. Did deep learning win because it's the absolute best way to create intelligence? Or did it win because it was just the luckiest?
This is the concept of the hardware lottery proposed by Sarah Hooker. It is a brilliant paper from 2020. The core argument is, we use deep learning because it runs great on GPUs. GPUs are great at matrix multiplication. Deep learning is all matrix multiplication. It's a perfect fit.
But GPUs were built for games, not brains.
Exactly. Imagine a timeline where we never invented the diesel engine, only electric motors. We would have built completely different vehicles. We might never have built semi-trucks. We might have built something else entirely. We build the models that fit the chips we have.
So you're saying there might be a superior form of AI, maybe something that works more like a biological brain or uses analog signals, but we aren't discovering it because it doesn't run efficiently on an NVIDIA H100.
That is the chilling thought. We might be stuck in a local maximum. Deep learning is incredible, don't get me wrong, but we should be humble. We didn't necessarily find the universal solution to intelligence. We found the solution that happened to win the lottery of the hardware market in the early 21st century.
That is really humbling. We're riding a wave that started because kids wanted to play Quake.
And that wave has carried us incredibly far. But it's worth asking what shores we aren't seeing because of the boat we chose. It suggests that the next big breakthrough might not come from making models bigger, but from a completely different hardware paradigm that unlocks a totally different type of algorithm.
So to recap for everyone listening, the resurrection of deep learning wasn't magic. It was a grind. It was 2 harsh winters, followed by a perfect storm of gaming hardware, internet-scale data, and some very clever math like ReLU and dropout.
And the core insight is depth, the hierarchy, stacking simple patterns to create complex understanding. That is the secret sauce.
And a little bit of luck with the hardware.
Out of luck.
I love that. It makes you wonder what the next abandoned idea is that's just waiting for the right hardware to come along. Maybe we should go dig through some papers from the 1970s.
You never know what you might find.
Thank you for unpacking this with us. It's wild to think about how fragile this history really was.
It's been a pleasure. It really shows that in science, timing is everything.
Absolutely. And to you listening, thanks for diving deep with us. Keep questioning the black box, and we'll see you on the next one.